Since we talked about realistic refrigeration cycles, now we should probably talk about unrealistic refrigeration cycles that we can actually analyze a little bit. So let's say we have a refrigeration cycle that undergoes the following steps. So let's say we start with, oh no, we'll start here. We'll call this point 1. So let's say we start at point 1 and we isothermally compress our ideal gas. So we take our ideal gas, we compress it slowly enough that it's staying at room temperature the whole time. Because, if we did that adiabatically, it would heat up. But if we do this really slowly, we can slowly let heat flow out and keep it at room temperature. And we do that up to point 2. At point 2, we then quickly expand our gas, which is adiabatic and is going to follow a steeper curve back down. And we're going to do that until we're at the same volume as point 1. And then, now, if we have done this correctly, we will end up at a lower temperature. So now, if we look at our isotherms, right, number 1 to 2 is the isotherm. 3 is on a different isotherm at some different temperature. And now we can have heat flow from the room or from the inside of the fridge into our ideal gas. And in that process, our ideal gas is going to heat up and we're going to end up back at point 1. So this is our refrigeration cycle. So let's throw some numbers up here and turn this into an actual problem. So we have some volume V1, some volume V2. I should label my axes. We'll say number 1 is at atmospheric pressure. So pressure 3 is somewhere below that, pressure 2 is somewhere above that. And let's say that V1 starts at 1 liter of volume. And let's also say that, since we have one more degree of freedom here, let's say that our hot temperature is 300 Kelvin, so that's room temperature or a little bit warmer than room temperature. And our cold temperature, we want the inside of our fridge to be at, where did I write that down? 260 Kelvin, which is minus 13 degrees C, so you can at least make ice cubes. Okay, so what is our coefficient of performance given what we know? All right, so I'm gonna make a little table of our points 1, 2, and 3, and the pressure and the volume. We're gonna have to erase some of this at some point. So at point 1, we know both the pressure and the volume. Pressure is 1 atmosphere, the volume is 1 liter. At point 2, we know neither. And at point 3, we at least know the volume is still 1 liter. We do not know the pressure at point 3. Okay, so before we jump into this, I also just want to think about, again, what's happening during these different steps. So from 1 to 2, we are doing work on our system and heat is coming out. From 2 to 3, our system is doing work, it is expanding, and it is doing work. We are doing negative work on it. And in the process, no heat is flowing because it's adiabatic. And from 3 to 1, we have no work because it is isochoric, and we have heat entering our system. We have a positive heat flowing into our system. Okay, so we could start a few different places. I think the easiest thing to start with is to find the pressure at point 3. So let me motivate it with this. Point 1, we know everything, right? So we can look at getting to things relative to point 1, moving from point 1 to somewhere else to figure out what's going on. And whether we figure out, we can start finding points in either direction. We don't have to follow the arrows. So we can find 3 from 1 because we do our process backwards on paper or whatever. Anyway, so the point is, we know 1, we want to find 3, we can do that first. So this is isochoric. So for isochoric transitions with V constant, we know P1 over T1 is equal to P3 over T3. So rearranging for P3, we get P3 is equal to P1 times T3 over T1, which is equal to, so T3 is the lower 260 Kelvin temperature. So we have 260 over 300 times P1, which is 1. So this is equal to 0.87 atmospheres, 0.8777, or sorry, 0.8666 atmospheres, I believe. Yes, and that is P3. So here we put in 0.87. Okay, so we know this now also. Right, 1 down, 2 to go. So now we want to find what's going on at 2. Without knowing the volume, it turns out we can't figure it out from this isothermal path. It's easiest to do the adiabatic path from point 3 backwards to point 2. So for adiabatic, it turns out we have a relationship for the pressure and volume, but it is not P1 V1 equals P3, or sorry, we're doing 2 and 3, so it is not P2 V2 equals P3 V3. It is PV to the gamma equals PV to the gamma, and if this is air, if this is an air cycle, I guess I should have said that in the beginning, that gamma would be for a diatomic gas, so gamma would be 1.4. That is 7/5. Okay, so plugging in numbers for this, we, I did the wrong one. Am I going to edit this out, or am I going to make you all watch this whole thing? We don't need to know. So it turns out that relating P and V doesn't work because we know neither P nor V at point 2. So we have to use a different relationship for adiabatic variables for the temperature, and that is T V to the gamma minus 1 is a constant. So that means T3 V3 to the gamma minus 1 equals T2 V2 to the gamma minus 1. All right. I haven't made that many mistakes that big on video, so this is kind of unfortunate. So we want V2, because we know T2, right? T2 is still 300 Kelvin. So V2 to the gamma minus 1 is equal to T3 V3 over T2. And now we need to take the gamma minus 1 root of everything. So we have V2 is equal to T3 over T2 to the 1 over gamma minus 1 times V3. Okay, so for numbers here, gamma minus 1 is 0.4, right? So these were to the 0.4 power, and so if we want to invert that, we have to put them to the 1 over 0.4 power. So 1 over gamma minus 1 is equal to 2.5. So V2 is T3 over T2, that is 260 over 300 to the 2.5 times V3, which was 1 liter. So for that, I get 0.70 liters, it's 0.699 something, I think, and that is V2. So you see, we're not actually compressing our gas percentage-wise all that much. We could get a much bigger change in temperature if we compressed it a lot more isothermally and then adiabatically expanded it a lot more. We would get a pressure drop to a much lower, isotherm if we had a bigger ratio of V's. Okay, so that is good for that. And lastly, we want to find the pressure at point 2, and now we can look at this isothermal isothermal compression from point 1. So P1 V1 equals P2 V2 for isothermal processes. P1 is equal to 1 atmosphere, V1 is equal to 1 liter, P2 we do not know, and V2 is equal to 0.7. So P2 is just equal to 1 over 0.7, which is 1.43 atmospheres. Okay, so we are now done with the cycle part of this, and we can start looking at what we need for our actual coefficient of performance. So our coefficient of performance for this cycle, if we're looking at it as a refrigerator, is going to be the cold heat, the heat going into it from the cold reservoir over the work, the work that we have to put into it. So this heat is the heat entering our system between 3 and 1, right? Well, we don't have any heat from 2 to 3. The only other heat is going from 1 to 2 during our isothermal compression, and that is heat flowing out of our system into this 300K room. So, so the heat entering our system to go from 3 to 1 is what we're interested in, right? Entering our system means leaving the room, means cooling the room down. So QC is equal to Q from 3 to 1. And the work into our system, well, we have work done on our gas going from 1 to 2, compressing it, but we get some of that back when our gas expands going from 2 to 3. So the net work is really this work that we do from 1 to 2 minus the work from 2 to 3. And I should say the way I've defined these are for work done by the system. If this was defined with our, if our W's were defined as work done on the system, we would have another minus sign here, and you can think for yourself why that is. Okay, we're ready to figure this out. So we want Q for 3.1, and we want the two works. So Q for 3.1 is easy because this is a isochoric expansion, right? So it is just NCV delta T. Our number of moles we do not have, but we can figure this out because that is PV over RT at any point we pick, and now we know all of the points, so we can just pick anything. So if we do that, the easiest thing to do is our pressure at point 1, so that's 101.3 kilopascals times our volume, which is 0.001 liters, over R and 300 Kelvin. That gives me 0.041 moles. So this is equal to 0.041 times CV, which is 5 halves R, times delta T, which is 260 to 300, gives me 40 Kelvin. And with those numbers, I get a heat in of 33.8 joules. So that is how much heat we can remove from our cold reservoir, and therefore is leaving our, leaving our refrigerator. Okay, all right. So we also want to figure out these works. So the work done between 1 and 2, this is isothermal work. So that equation is PV log V final over V initial. So here this is 1 atmosphere times 1 liter times the log of V final over V initial. So that's the log of 0.7 over 1. So for that, I get minus 36.1 joules of energy. And this is negative because now, again, we're defining W as work done by the system, which means to compress it, we have to do work on the system, which is negative work done by the system. Okay, so this is work 1, 2. Lastly, is work 2-3, we get some of this energy cost back. And our equation for work done by an adiabatic process is P final V final minus P initial V initial over 1 minus gamma. So that is, this is a long thing, but we're gonna write it all down. So I'm gonna do the top in liter atmospheres and then convert it. So P final V final is, so that is at 0.3. So that's 0.87 times 1 minus P initial V initial, which is at 0.2. So that's 1.43 times 0.7. And I need to convert units. So to convert my atmospheres, I need to multiply by 101,000. And to convert liters, I need to multiply by 0.001 and divide all of this by 1 minus gamma, which is minus 0.4. And plugging all those numbers in, I get positive 33.2 joules, which means that from 2 to 3, our system does positive work on the environment. So the net work done by our system is 33.2 minus 36. I'm gonna write W net by the system. So again, that's 33.2 minus 36.1, so that's minus 2.9 joules, which means the net work we do on the system, which is really our cost, is plus 2.9 joules. That's how much work we have to put in. And now we are done. We just have to divide. So we do 2.9 joules of work, and in the process, we are allowed to move, what was it, 33.8 joules of heat in the process going from 3 to 1. So this gives us a coefficient of performance of 11.7, which is very big. A couple of okay, so this is the end of the problem. 11.7 is the correct answer. Of course, this is unrealistic for what we get in an actual system. There are lots of reasons for that. One is isothermal processes are really slow, and generally you try to avoid them in real systems, because to move it slow enough that your gas really stays at the same temperature, you are not going to be moving very much heat in a particular amount of time. So that's an example of one part of this that's a problem. But other than that, I think that's all the analysis to do. Oh, well, yes, there is one other problem, and that is at 0.3, when we add some heat, our temperature at 3 increases, right? So we add a little bit of heat, we go from 260 to 261. We add a little bit more heat, we go to 262. And the last part of our heat is delivered at some higher temperature, right? We're putting heat in at 290, we're putting heat in at 291. So really, if we were trying to keep our fridge cold, we wouldn't be able to flow in heat at these higher temperatures, because the inside of our fridge is already colder than that. So processes like this, where the heat is going in at a bunch of different temperatures, also tend to cause practical efficiency problems, because the inside of your fridge is not it's not going to raise its temperature along with you as the temperature of your gas increases. So you're only going to be able to put in some fraction of this 33.8 into your working fluid, your ideal gas.